Hello everyone, welcome to our final lecture, our last lecture, and today we'll be learning about other data structures. What other data structure we have? So let's get started. So here we have binary search trees, first of all, which is an essential data structure in computer science. A binary search tree, as the name suggests, is a type of binary tree that is specifically organized to allow efficient searching, insertion, and deletion of values. What makes it special is its ability to let us search for any value stored at any node in the tree. When working with binary search trees, we usually search for a particular key value. Once the corresponding node is located, we can retrieve all other information stored at the node. So this efficiency makes binary search trees a preferred choice in many algorithms and real-world applications. One key assumption in binary search trees is that all the values we search for must be distinct. This ensures the structure and functionality remain predictable and optimized for operations. Now here, properties of binary search tree. Like a binary search tree does not have to be a complete binary tree like a heap. For any particular node, the key in its left child, if any, is less than its key, and the key in its right child, if there is any, is greater than its key. So here in this code, we can say we have a template class data type, that then binary search tree node like BST node, and then data type info, BST node data type left, BST node data type right. So the implementation of a binary search tree usually just maintains a single pointer in the private section called root to point to the root node. So here we have an example of inserting nodes into a binary search tree. So how we can insert a node into a binary search tree? So let's say BST starts off empty. Now we have root and then null. There is no node here. So objects that need to be inserted, only key values are shown. So these are the values that needs to be inserted in this tree. So we will insert these nodes into a binary search tree. So let's get started. First we are inserting 37. So in the previous slide we saw that there was root and then null, means there was no nodes on the tree. Then we inserted 37 first here after root. Now we have 37 and root is indicating to 37. Now if we calculate the two for the second one, so we have the second one. Now we want to insert 2 right now. Now we'll check if 2 is less than 37, then it will insert 2 on the left side of 37 as per the requirement. Okay, so then we are inserting it on the left. Next 37 is indicating, 37 is the parent of 2, and then root is the parent of 37. Now next for 45, we'll check if 45 is greater than or less than 37. So 45 is greater than 37, so it will insert it at the right of 37 like that. So here we have 45, which is the right child, and 2 is the left child of 37. Now let's compare 48 now. When comparing, we always start at the root node. So here 48 will compare with 37, that 48 is greater than or less than 37. So look to the right. here 48 is greater than 37, then we will go to right. Right means 45. So this time there is a node already to the right of the root node. We then compare 48 to this node. So as we started from 37 and 48 is greater than 37, so it should be inserted on the right side of 37. But if as we have already a right child which is 45, so then it will compare with 45. Now after we'll compare with 45, it will say that 48 is greater than 45, and then 45 has no right child, so we'll insert 48 on the right of 45, like that. Okay, now next we have 41. So first we'll start from root. So 37 is the root, so we'll see 41 is greater than 37. So look to the right. We were searching if there is any right child, so we already have 45 which is on the right, so we'll compare it with 45 next. So we'll check with 45. Now 41 is less than 45, and we'll see if there is any left child for 45, but there is no left child, so we'll insert here. Now next is 29. So we'll check with 37 first. 29 is less than 37, but we already have a left child on 37, so we'll compare it with 2 here. So 29 is greater than 2, so we'll check if there is any right child. There is no right child for 2, so we inserted 29. Okay, next is 20. So we check 20 is less than 37, so it will go left. So we already have 2 on the left, so we'll check with 2, and 2 is less than 20. So because 20 is greater than 2, so it will go right, but we already have right child which is 29, so it will check with 29. So it will check with 29, and 20 is less than 29, so it will go left, like that. Now next is 30. Now here 30 we'll check if 30 is less than 37, so it will go left, but we have 2 on the left, so we'll check if 30 is greater than 2, which is true. Now it will go right, but we already have 29 on the right, so it will check with 29, and 30 is greater than 29, so it will go right here. Okay, next is 49. So 49 is greater than 37, so it will go right, but we already have 45 here, so we'll check, and then we'll see 49 is greater than 45, so it will go right, but we already have 48 on the right, so it will check again 49 which is greater than 48, so it will go right here. Okay, so next is 7, the final one. Now 7 is greater than 37, so it will go left, and then it will check with 2 again, and which is 7 is greater than 2, so it will go right, and then it will check with 29. It will go left, where we have 20. It will check with 20 again, which is less than 20, and it will go left. So this is our final. So all elements have been inserted, and this is our final binary search tree. Now searching for a key in a binary search tree uses the same logic. So we just inserted all these nodes. Now if you want to search anything from this binary tree, so we'll also use the same technique. Like if it is greater than the root, it will go right, and if it's smaller than the root, then it will go left. So we'll use the same logic. So let's see another example. So key to search for, we want to search for 29. So let's start the search. First we'll start with root. Root is 37, so it will check 29 is less than 37, so it will go left. So left we have 2, so it will check with 2 that 29 is greater than 2, so it will go right. So here we already found it. It is that easy. So let's say we want to search for 3. We don't have 3 here, so let's say we want to search for 3. How we can get 3? So start with root, we have 37. 3 is less than 37, it will go left. Now 3 is greater than 2, it will go right. Then 3 is less than 29, so it will go left, where we have 20. And 3 is less than 20, it will go left. So we have 7 here. Now 3 is less than 7, but there is no other node left. When the child pointer you want to follow is set to null, the key you are looking for is not in the binary search tree. That means the key you are looking for is not in the tree. So that is how we are getting a null value. Okay, so if the binary search tree happens to be a complete binary tree, the time for insertion is big O log n. The time, theta log n, and the time for the search is big O log n, similar to swapping upwards or downwards through the heap. However, we could run into some bad luck, like sometimes it could be some peculiar type of tree which we can have more that can consume more time than usual. So here we have exactly the same keys were inserted into this BST but you see, this is kind of a peculiar tree. There's no left child here, everything is on the right. So exact same values or nodes are inserted, but in a different order. But they were inserted in a different order, that the order shown below. Like it's inserted first 2, then 7, 20, 29, everything is bigger. So it's incrementing. So in this peculiar tree, we could have a more time complexity. So this is some bad luck. So a BST can be performed this way, but sometimes if we found this kind of a tree, that could be a bad luck. That will take more time. So using the tightest possible big O notation, the insertion and search time is big O n. Okay, now see a critical distinction in binary search trees, like balanced versus unbalanced. A binary search tree is considered balanced when its operations such as insertion and search take logarithmic time. So here which is represented as theta log n. This balance ensures that the tree remains efficient with its height minimized relative to the number of nodes. And balanced trees such as AVL trees or red-black trees achieve this efficiency through specific rules or rotations that maintain their structure. On the other hand, an unbalanced binary search tree lacks this efficiency. When the height of the tree grows disproportionately relative to the number of nodes, it can degrade to a linear structure, leading to insertion and search operations taking big O n time. This often happens when nodes are inserted in sorted order, formatting what resembles a linked list. Now this distinction between balanced and unbalanced trees significantly impacts performance, specifically when handling large data sets. Ensuring balance in a binary search tree is critical for maintaining its intended efficiency and scalability. Okay, now we'll see deleting a BST node. How we can delete? So we just saw insertion and searching operation. Now we'll see deleting. How we can delete a node? So deleting a node in a BST is a little tricky. It has to be deleted so that the resulting structure is still a BST, with each node greater than its left child and less than its right child. Now deleting a node deleting a node is handled differently depending on whether the node has no children or has one child. So let's see, or has two children. So depending on this type of option, it is the handling of we have to handle it differently. So let's see an example. Excuse me. Deletion case 1, no children. If there is no children, how we can delete? So node 49 has no children. If you look at for node 49, it has no children. To delete it, we just remove it like that. So we just remove it and it's gone. Now node 48 has one child, which is 49. To delete it, we just splice it out. So we'll just replace the child 49 into its parents place, which is 48. So when you will delete 48, 49 will be in this place like that. Now another example for node 2, if we have node 2 has one child, to delete it we also splice it out like that, because 29 is also less than 37, so we can do that like that. So we are deleting 2. Now deletion case 3, if we have 2 children, node 37 has 2 children, which is 2 and 45. Now how we can delete 37? To delete it, first we find the greatest node in its left subtree. So left subtree means we start from 2. First we go to the left ones, then follow the right pointers as far as we can. Okay, now we go to 2. 2 is the left one, so we'll go to 2. Then from 2 we go to right, so we have 29, and then right, another right is 30. Then 30 is the greatest node in the left subtree of node 37. So next we copy the object at node 30 into node 37 like that. So we copied 30 to 37. Finally, we delete the lower red node using case 1 or case 2 deletion like this. So we have 30 on 37 place because we deleted 37, but we made sure that the binary tree has its own structure. So let's delete node 30 now. So we'll do the same thing. We'll go left, then we'll go right, and then there's no other right. The greatest node in the left subtree node of 30 is 29. So we'll just copy this again, and then this time the lower red node has a child, one child, which is 20. So 20 will go to 2. To delete it, we use case 2 deletion, which is we are just placing 20 under 2 like that. So it's deleted. So in all cases, we must find the node we wish to delete first using the standard search method. Finding the greatest node in the left subtree is just a continuation of a path down the BST. For balanced BST, the time complexity for deletion is big O log n in all three cases. For unbalanced BSTs, the time complexity is big O n in all three cases. So why use BSTs? Why are we using those? Well, hash tables can search in theta 1 times, so why use BSTs? BSTs have the ability to provide all keys in order in theta n time. That's why we are using BSTs. Okay, now we'll see graph. Graphs are a very general data structure. We all know about graphs. We all learn about graphs from our school. So a graph consists of a set of nodes called vertex. Any vertex can point to any number of other vertex. It is possible that no vertex in the graph points to any other vertex. So we'll now see an example that will be clear for you. Okay, here we have each vertex may point to every other vertex even if there is thousands of vertex. Okay, now let's see the example. This is a directed graph. So directed graph means there is a direction. Which node is pointing to which node? So it is so each pointer is called an edge. So here, if you look at here, A is pointing to D, D is pointing to B and F, and then B is pointing to C and E, and then E is pointing to F and D, and C is not pointing to any node. So that is called a directed graph. Now this one is an undirected graph. So there is no direction here. Each edge points in both directions. So A points to D and D points to A. There is no direction given. So this is an undirected graph. Now this is another D graph, means directed graph. Here nodes A and F point to each other. It is considered improper to draw a single undirected edge between them. Now this is a weighted graph. Weighted graph means let's say we have some city like Grafville, Node Town, Vertex City, Builder's Paradise. Let's see that is a city. Now in this city we have 1, 2, 3, 4, 5, 6 places. Now if you count these numbers as the distance as mile, then that you will see the distance. Like if you want to go from Builder's Paradise to Vertex City, it takes 4 miles if you go by car or whatever it is. So let's say it takes 4 miles to go there. Then if you want to go from Vertex City to Binary Tree Valley, it takes 10 miles to go there. So using those values, you can calculate the distance between two places. So this is called a weighted graph. So from this graph you can find a shortest path to go to some place. If you want to go from Builder's Paradise to Pointerberg, then you can go to any you can go to multiple ways, but if you want to search or if you want to find the shortest path, then you can just calculate like if you go from Builder's Paradise to Vertex City first, that is 4 miles. Then if you go to Grafville, then 4 miles, total 8. Then if you go to Pointerberg, then that will be 8. So 8 and 8, 16. But if you go to node town, which is 3, and then come to Pointers Park, that is 7. That means that is total 15, so which is smaller than 16. So you can use that path. So that will be the shortest path to go from there. So in that way we can use a graph, weighted graph, to calculate our this kind of, we can solve this kind of problem. Now a vertex A is said to be an adjacent to a vertex B if there is an edge pointing from A to B. Graphs can be implemented in a couple of popular ways. First is adjacency matrix and adjacency list. We'll also see these examples. First is adjacency matrix. Nodes are given a key from 0 to n minus 1. The adjacency matrix is a two-dimensional array of bool type variables. Now let's see an example here. Now if you look at here, we have true, false, all this, the whole table here, and then on for row we have 0 to 5, and for column we have 0 to 5. Now from here, the row numbers give the vertex numbers of the vertex that an edge is pointing from. So for example, node 1 points to node 2, set to T. Now if you look at here, node 1 points to node 2. So we have T here, we found T. This is the T, this is the connection we found. Then node 2 doesn't point to node 1, so it is false. So node 2 from left, the left one, node 2 is pointing, it's not point to node 1, so it is false. Note that we can construct a graph from the adjacency matrix. The vertex may not be drawn in the same locations as the original graph, but the connections will be the same. So using this graph, we can have an adjacency matrix, and using a matrix we can also draw a graph. Okay, now let's see adjacency list. An adjacency list is an array of linked list. The vertices are numbered 0 through n minus 1. Each index in the array corresponds to the number of a vertex. The vertex with an index number is adjacent to every node in the linked list at that index. Okay, let's see the example. So it is a linked list kind of orientation here, which is the adjacency list. Now here vertex 1 is adjacent to vertex 2, and vertex 1 is also adjacent to vertex 5. That's why we have 2 and 5. Now vertex 2 may not connect to vertex 5 in the graph here. You see, 1 is connected to 2 and 1 is connected to 5, but 2 is not connected to 5. That is not requirement. Then if you look at here, vertex 3 has an empty linked list. It is not adjacent to any other vertices, so it is not connected to any other node. Then if you look at the red font, which is for vertex numbers, black font is for weights. So these are the weights, so it is a weighted vertex adjacency list. So here ordinarily the vertex info is not stored in a linked list node of an adjacency list. The vertex info size may be huge, and many duplicates of it would be stored throughout the adjacency list, wasting space. Instead, a separate array contains the vertex info objects. Each index corresponds to a vertex number for easy lookup. So here we can say, what is the difference between matrix and list? So the speed of the adjacency matrix or the adjacency list depends on the algorithm. Some algorithms need to know if there is a direct connection between two specific vertices. the adjacency matrix would be faster for that. And for some algorithms which are written to process the linked list of an adjacency list node by node, the adjacency list would be faster. So it is we cannot say which one is better. It's always depends on the algorithm. So whatever algorithm you're using, depending on the algorithm, for some algorithm adjacency matrix is faster, for some other algorithms adjacency list would be faster. So both are equally important. So that is all for our today's lecture. That is the end of our course, and I already posted an announcement about our final exam, which is coming next week. So if you have any question about the exam, please let me know, because I will not accept any request for extending the date or extending the time for the exam, or I will not take that exam any other day again. So if you miss the exam, or if you have any problem on the exam day or any kind of problem, please feel free to contact me before the exam, so that we can if possible I will find any solution, but not on the exam day or after the exam. Also so as the exam will be open available all day, but you can pick any time as per your availability from all day, from the whole day. So you can pick your 2 hours. But once you started the exam, you have to finish it, or otherwise it will auto submit, and you can only attempt once. So please make sure you start before prior to 2 hour prior to the end time, because when the exam time ends, it will automatically submit it. And don't wait for last minute or last hour, because you could have some internet problem or any other problem which I cannot consider on that time. So please make sure you start your exam don't waste for the last hour. That's it. So let me know if you have any kind of question or concern, and throughout the course whatever you felt, you have the evaluation form available for the course. So make sure you fill up the evaluation form, and let me know if you have any question. Thank you.